Okay, we have started the recording and I'll start the backup also. Okay, we are set. All right, so let's begin this second live session of week number 12. So in the previous class, we started with this new chapter on buckling. And first we considered this relatively simple situation considering two rigid links. And then we went on to an actual example of a vertical beam, which we called, which is referred to as a column. And then we went about determining the critical load at which buckling will occur. So we solved this differential equation and through some conditions, we arrived at this one. We arrived at this particular this formula referred to as the P critical. This is the Euler's load or the Euler's critical buckling formula. And I had mentioned at the end that please do not forget that this formula is only and only for the pinned end, meaning that when our column has exactly these kinds of boundary conditions, that at one end it is pinned and the other end also it is pinned, only and only then will you have the critical buckling load of this particular form, which naturally brings us to the question that what will be the formula for situations where the end conditions or the boundary conditions are not pinned, rather something else. And that will be the topic of discussion for today's class. Okay, so the first case that we are going to consider beyond the pinned case is this one. So we'll again consider a vertical beam or column, but this time the bottom end, unlike previously when it was pinned, we are going to clamp it to the ground. So this end is clamped, the other end is kept free, but free in the sense that you will still have a vertically acting or vertically downward acting force being acting here. So under the action of this force, there is a possibility that some kind of instability will occur, and this straight configuration will no longer remain straight and it will undergo some kind of buckling. So let us consider such a buckled shape in exactly the same kind of fashion that we had considered earlier. So earlier also we had considered, we had started our derivation by considering this kind of a buckled shape, and it was referring to that buckled shape that we carried out our derivations. In exactly the same spirit, we will proceed for this particular case also. So what we say is that let this column get deflected in this particular fashion. The load continues to act like this, and so this is the deformed configuration. This is what we say is that this thing has buckled. Please note that the shape of this or the buckled shape of this column is qualitatively different from what we had earlier. And there is a distinct possibility that the critical buckling load when such a shape occurs is also going to be different from what we had obtained at the end of the previous class. So how do we go about doing this? Now, there are different ways of doing this. Okay, so the way that this problem has been addressed in our textbook by Beard Johnson et al. Is that they have not actually directly solved this problem. Rather, they have drawn an analogy of this situation with the previous situation. So the previous situation, just to briefly recap on the same page, was this situation or maybe this situation. I mean, it was buckling like this, but there is absolutely no difference whether it buckles like this or it buckles this way. Okay, there is absolutely no difference. It's the same thing. So I will consider it like this just to maintain the same kind of nature as this one. Okay, its shape is like this. That's why I'm also considering this concave to the right shape. And now you try to draw some kind of an analogy between this and this. If you are a little bit imaginative, and this is the kind of argument that is presented in Beer and Johnson, is that this shape, okay, it can be considered to be half of this shape. Why they are saying like that is because this thing has perfect symmetry about the horizontal axis. So if you draw an axis about through its midpoint, you will see that at this midpoint, this slope here is 0. Similarly, the slope here is also 0. The reason is that it is clamped to this ground. Okay, because it is clamped to this ground, the slope here is 0. So it is as if this particular part is like this particular part, and this entire shape is like this entire shape. Now, if you ask me, this is not a very good technique of solving a problem. I mean, it's a clever way of doing it, and it kind of matches. Okay, the answer that they get for the critical load, it kind of matches. I mean, it matches perfectly. But personally, I think this is a very it's a clever way of doing it, but it's a very lazy way of doing it. Okay, we should not be doing things like in this kind of a lazy fashion, especially because when we do like this, we miss out on a significant amount of the understanding which is required towards the mechanics of the problem. Okay, there's certain things going on here in terms of the actual mechanics. It's not just the geometry. Okay, it's not just about the shape. So we miss out on that information if we proceed like this. So that is why I'm going to present the solution to this in a slightly different fashion. Okay, but just for the sake of completeness, I will mention here that in Beer and Johnson, if we proceed by their argument, you can clearly see that earlier this entire length was L. Okay, this entire length was L. Now this length is L, and if you keep on drawing this thing, if you extend it like this particular thing, this is the effective length of such a situation. Okay, the effective length, it becomes twice L. Okay, so let me just write it here that L effective becomes twice L. And just remember this thing. You will see at the end of the solution through the proper technique that I'm going to tell you, you will also end up with such a thing. But that's a proper method. So how should I proceed here? Tell me. I'll give you one piece of information, one key piece of information, and that is that if you compare with the undeformed configuration of the beam, like here, undeformed configuration of the beam, then the amount of deflection this thing has undergone, I'm telling you that piece of information. Okay, so let this be delta. Okay, and just like before, we are going to say that so this is X and sorry. This thing is X and this thing is Y. Okay, so the deflection is captured by this variable Y. At X equal to 0, Y is equal to delta, and this downward, this along the length of the beam, we have the coordinate variable X. So just like before. Now you tell me what should be my first step if I proceed like before. So earlier I had considered the expression for the moment. The expression for the moment and any generic cut section. So I will take a generic cut section here and I will consider the free body diagram of that part. We have the force P here. We are also going to have a bending moment like this. For the sake of completeness, you can take this V, and then what else? We will have nothing else here. Okay. And now if you consider the balance of the moment, what are you going to get? So please tell me. What will be the expression of the M? Please be a little bit careful, but you know how to do this. Okay, so this, see, from the undeflected position, this distance is delta. And this is at a generic cut section, that distance is y. Now you tell me, what should be the expression for M?
So P times delta minus y.
P times delta minus y. Very good. Okay, and this should be actually positive. Okay, so because this is in this kind of an anti-clockwise sense and this is clockwise, so this is perfectly all right. M is equal to P into delta minus y. Now all that we have to do is go back to our trusted equation, which connects the moment with the curvature. This thing.
Sir?
Does anyone want to say something?
Yes, sir.
Yes, please tell me.
Yesterday you had told me to remind about that hemispherical belt thing.
Right. So yesterday, after the test, Daivik had mentioned some issue with the question number 1 of the part 1 of the test. Okay, so okay, I'm just digressing a little bit here. Okay, so test 2 part 1 question 1, that question on the thin walled pressure vessel. So Daivik had mentioned that for the calculation of the thickness of the hemispherical head, he had considered the weld strength. Now, when setting the question, we had not considered that, and people who have done like that got the correct answer, because we have also not considered the weld strength for the hemispherical head. So by default, I mean, that part of the answer, most of them got correct. Okay, but those who had thought a little bit more deeply and did consider the weld strength got a different answer, and they got it wrong within Moodle. Okay, that does not mean that what they have done just by thinking too much about the problem is wrong. That is why I'm going to try to manually override. Okay, I don't know whether it is possible in Moodle or not. If it is not possible, I'll just make down a note of the name and roll number of the student and adjust the marks accordingly, whoever has done the calculation correctly. Okay, so I had given a deadline up to 10 o'clock today to mention within that thread that Daivik had initiated, that, I had initiated actually later on, that you please mention if you have done the same kind of thing as Daivik. Okay, and quite a few students have already posted that they have also done the same kind of thing, and I'll be attending to their issues fine. In case someone has not yet seen that thread, please do see it, and if you have done the same kind of thing, please just mention. Okay, small mention that you have also done the same thing, so I'll be able to address everyone's issues together. Okay, so maybe sometime in the afternoon I'll sit with it, so please try to finish it up before that. Okay, all right, let's get back to it. So we have this equation. Now, just like before, we are going to rearrange this. And this particular combination P by EI, that's a positive entity, and we are going to represent it by K square. So in the previous class, we had gone about determining the solution of this through a laborious first year maths kind of way. We are no longer going to do that because I want to talk more about the buckling thing rather than just doing the maths thing. So in the interest of saving time, I will just give you the solution, but you can verify through complementary function and particular integral that this solution is indeed correct. Or if you can just substitute it, then also you will be convinced that this is actually the solution. So this part of the solution is the same, the homogeneous part of the complementary function, a sine kx plus b cos kx, and extra thing that you are going to obtain is this thing. Okay, because this right hand side is not 0, you're going to get this extra term. So this is the solution to this differential equation. Of course, this is not the complete solution because we still have this expression in the form containing the unknowns a and b. Now, what do I do in order to say something about a and b? Earlier, I had used the boundary conditions, and that is exactly the same kind of thing that we're going to do again. So tell me what boundary conditions I should be using. Tell me.
So y is equal to delta at x equal to 0.
Okay, that is one condition definitely. We are going to use it, but tell me, is it not absolutely clear that at x equal to L, we have y equal to 0 as well as x equal to L dy dx equal to 0? Okay, there is absolutely no doubt about it. There is also no doubt about this delta, but the reason that I'm not going to go down that route right now is that I want to keep my answers involving the delta, and later on I somehow want to get rid of it. Okay, so let me not get ahead of myself. You will see what I'm going to do. Okay, so let's proceed by considering the two boundary conditions at x equal to L, y equal to 0. So boundary conditions. If we do that, then remember our expression is a sine kx plus b cos kx plus delta. This is y. So if we just substitute x equal to L, this becomes a sine kl plus b cos kl plus delta is equal to 0. Next, at x equal to L, we have dy dx is equal to 0. Now dy dx is equal to, ak cos kx minus bk sin kx. Delta is just a constant, so that gets differentiated out. So what we have from here is this ak cos kl minus bk sin kl equal to 0. And that gives us what? It gives us a is equal to b tan kl. Okay, please verify. Okay, this is the thing. Okay. So let's go back to this equation. Okay, so let's go back to this. So what you're going to obtain is, if you substitute a is equal to b tan kl, so this is b sine square kl divided by cos kl plus b cos kl plus delta equal to 0. So basically, if you just multiply throughout, you will get this thing as b, because this is b sine square kl plus cos square kl, that is b plus delta cos kl. Okay, I'm skipping a step or two in between. Okay, I hope you don't mind. So this is this becomes b is equal to minus delta cos kl. Okay, now so let's write this. B is equal to minus delta cos kl. which means that A, if we substitute this thing here, we are going to obtain A is equal to what? Minus delta sine k. Is it not? All right. This expression of B and A, whatever it is. So now our y becomes what? Y was A sine kx plus B cos x. So A is minus delta sine kl sine kx, and B is where is B? B is minus delta cos kl, and this is cos kx plus delta. So this is minus delta sine kx kl plus cos kx kl. So can you tell me through trigonometric identity what this is?
Cos of kx minus k.
Minus L. K times x
Cos
minus
of k into x minus L or L minus x, doesn't matter, okay, because
Correct.
cos minus
Fine.
theta is cos of theta. So this thing, and yeah, this thing. Okay, so let me go to the next page, write it clearly. So y is equal to minus delta cos k L minus x plus delta. Okay, now we go back and just implement this condition that at x equal to 0, y is equal to delta. Let's see what happens now. So delta is equal to minus delta cos this is x. If you put x equal to 0 here, this is just cos kl delta and delta cancel from both the sides. So we have delta cos kl is equal to 0. Now you see, if you either delta equal to 0 or cos kl equal to 0. Now if you say delta equal to 0, fine, delta equal to 0, but that's just a trivial thing, because if delta equal to 0, the whole thing is not buckling. What are you going to do with it? Okay, so that's quite pointless to talk about. So from here we obtain that cos kl equal to 0. So tell me now, what should be the condition for this cos kl equal to 0 in general? What should be kl then? What form it should take? So earlier in the previous case, that pinned case, we had obtained sine kl equal to 0. Remember? So we had written that kl should be equal to n pi, where n is an integer. Now what should this kl be?
N plus 1 by 2 into pi.
Pi by 2.
It should be twice n minus 1 into pi by 2. Okay, so all multiples of pi by 2. Okay, pi by 2, 3 pi by 2, all those things. So just to make it clear, n is equal to 1, 2, 3, all these things. Now earlier in the pinned case, we had obtained this thing, and then for n equal to 1, we had considered the lowest value of the p critical. Okay, so we are going to do a similar sort of thing here also. But for now, we'll just keep on writing like this. That means this k is equal to twice n minus 1 pi by 2l. Let me go to the next page. Okay, let's put this n equal to 1. Okay, if you put n equal to 1, then k is equal to just your pi by 2l, and from here remember that our k square is equal to p by ei. Okay, just like before. So this thing is k square is equal to pi square divided by twice l whole square, and this k is so I'm just writing it, pi square ei divided by twice l whole square. So earlier we had obtained our p critical as pi square EI by L square. Okay, just see this thing at the end of the previous class, pi square EI by L square. That was the P critical. And now we are getting the P critical as pi square EI by twice L square. And in Beer and Johnson, just through some hand waving, they had said that L effective is equal to twice L. So that kind of makes sense. Okay, this L effective is equal to twice L. That makes sense. Because we have this, instead of L, we have this twice L. So that is why it is said that this L effective is equal to twice L for this kind of a column. All right. So does anyone have any confusion regarding this? If not, let us proceed. Okay, because I want to take up other cases also. So this was the this was one case. Okay, so let's say this is case number 2. This is our case number 1, the pin case. Okay. Let's take another case. This time we are going to consider okay, we are going to consider this. So just like before, we are going to clamp the lower end, and this end we are going to pin. Okay, so okay, we are using this kind of a guided support only to ensure that this doesn't move here and there horizontally. Okay, it only moves vertically, but as far as the rotation of this part or this end of the column is concerned, there is no resistance to its rotation. Okay, meaning that the moment here at this end is going to be 0. Please note that, please note that this case is significantly different from this first case. Not, I mean, certainly it is different from this one, but this case also it is different because this other end at x equal to L, this was pinned, but this case number 3, the one that we have just drawn here, it is clamped. Okay, so it is quite different. Now, if you refer to Beer and Johnson, they have done this problem. Again, I would say in a certain clever way, but that's not a very standard approach of doing the problem, I would say. Okay, rather, there is a more straightforward way of doing this problem. Okay, and as you go to the higher classes, you will see that it does make more sense to proceed in the way that I am going to show to you. Okay, and briefly, very briefly in passing, in the previous chapter, when we were doing the deflection of beams, I had mentioned, I don't know if anyone remembers this, I had mentioned that when we go on to the buckling of beams, time and again, we take the help of the 4th order equation instead of the 2nd order equation. So it is now time to fulfill that promise of showing you that the 4th order equation is actually quite helpful, and it helps it helps us to get to the solution in a direct fashion instead of arguing this and that. Okay, so the way we proceed here is like this. You see, this equation is valid. Okay, this equation is valid. Now, we had also said that from this we are going to obtain ei d square dx square, this m is equal to minus py. So this thing is like this. So this is exactly like before. Okay. But now, let's say we differentiate this twice. So first we are going to obtain this equation, and then we are going to obtain this equation. Now it may seem to you that we are behaving like as like plus 11 students just because we know how to differentiate. We are just differentiating things here and there. Okay, but there is a reason to this, and you will soon see this. Okay, in fact, I'm going to tell you right now. See, from here to here, we have not done anything extra. I mean, we have just differentiated twice. Okay, apparently nothing special is going on here. But this is a governing equation also, and this governing equation is of fourth order. Now, what is the principal difference in the solution methodology of a second order equation and a fourth order equation? You tell me, like the full solution of a second order equation and the full solution of a fourth order equation, what is the primary difference? You tell me. I'm waiting for answers. Please tell me. When you are trying to solve a second order equation versus when you are trying to solve a fourth order equation, I mean the full solution. Okay. So what is the principal difference between the two?
So we need to take boundary conditions.
Exactly. In terms of the boundary conditions, the fourth order equation is much more demanding. Okay. A second order equation only needs two boundary conditions, but a fourth order equation needs four boundary conditions. Now, try to think of it not just mathematically, but from a like a physical or a mechanical perspective. When you have a fourth order equation, and this fourth order equation is demanding you to satisfy four boundary conditions, it is as if this fourth order equation is asking you to fulfill all the mechanical requirements associated with this problem. At least more requirements considered compared to the second order equation. So second order equation is only demanding you, okay, it's kind of relaxed. You satisfy two boundary conditions, I'm happy. But the fourth order condition is saying no, you have to satisfy, in order to satisfy me, you have to respect two more boundary conditions. So it is as if it is asking you to respect the mechanics a bit more. And because it is doing that, you will see that at both the ends, you will be required to satisfy two boundary conditions. So two boundary conditions here and two boundary conditions here. And through that, the entire picture of this column is quite nicely captured compared to the second order equation, where you have to pull off some tricks to do this. Okay, in the previous case also, here you see, you may have had a nagging doubt. In fact, one of the students just had mentioned at the beginning that when we want to find out this A and B, we use at x equal to 0, y equal to delta. Now that's an absolutely valid argument. Why shouldn't we use that? We should try to think something like that. At least even if we don't use something like at x equal to 0, y equal to delta, we should be saying something about the mechanics which is happening at this end. Because I had started by saying that, okay, this is a free end or something is happening here, but I had not mentioned anything about the shear force or the moment at this end. Rather, I had just cleverly bypassed that end and just concentrated on this end and got some solution. I think it would have been far more complete and like a comprehensive thing to do if we had respected the boundary conditions here as well as the boundary conditions here. Then it would have automatically, whatever solution we would have done, it would have automatically captured the whole thing. That would have been a better thing to do. But that involves a little bit more math. I mean, and already I was deviating from Beer and Johnson, so I deviated to an intermediate level and did not go that far. But it can definitely be done. This problem can definitely be done in an even more systematic way than what I had shown you by considering a fourth order equation. Now, when we are coming to this case, this one I actually prefer to solve it by the fourth order equation, because I really want to respect all the proper boundary conditions associated with the mechanics of the problem here. So, but before we can start talking about the boundary conditions, we have to arrive at a certain form of the solution. So tell me, how should I go about doing it? First of all, I will just rearrange this thing in a form which is a bit familiar to us. Just like before, I have divided throughout by EI, and this P by EI, I'm saying that is equal to K square. So exactly like before. So this equation, you tell me how should I solve it? Well, as before, you can take this thing as y is equal to e to the power mx solution form. And if you do that, if you substitute this e to the power mx here, you are going to obtain m to the power 4 plus a square m square is equal to 0. Okay, I hope this is not too difficult to understand. If you substitute this thing here and this thing here, this gets differentiated 4 times, so 4 m's come out outside, and this thing just gives 2 m's. So you have m to the power 4, and this one has m square. So you have this form. So let me go to the next page and then just continue with the solution. This is m square times m square plus k square equal to 0. Tell me what should be the solution values for m?
Ik minus ik.
0 or plus or minus ik.
Plus minus ik. Plus minus ik is fine. That one all of you know. But is it just 0 or something else is also there? Actually, what I wanted you to say is that it is 0, 0, minus ik, plus ik. Okay, it does actually make a world of difference that this is a repeated root. Okay, you have studied this in your first year. Probably you have forgotten a little bit. Okay, so you have 4 roots of this. One of them is repeated. Okay, if you just say it is 0 minus ik and ik, then the form of that complementary function or the homogeneous part of the solution will be different from what it will be if you have a repeated root. Okay, so now you tell me what should be this thing. So I'm going to write it like this. This ik and minus ik and plus ik, that you know will contribute to this sine kx and this cos kx. Okay, so we have gone through this part earlier. But for this repeated root, what is going to happen? So suppose as you guys had mentioned just a minute earlier, if this had been actually 0 minus ik and plus ik, then the solution form would have been a sine kx plus b cos kx that you obtain from this and this, plus what? Basically, it is like this: c to the power e to the power 0 into x, right? So this is what? This is just c, just a constant, is it not? It's just a constant. But now you have a repeated root. So will it be just plus c plus d or something else?
Plus dx.
Yes. So it should be like this: plus cx plus d. Okay, so if some of you have forgotten why when a repeated root is there, why it is like this, I request you to please go back and refer to your maths notes from first year. Okay, so you have this thing. So now we have to say something about this a, b, c, and d by referring to the boundary conditions. So Just take a quick look here. In fact, I can copy paste from here to there. I'll just put this diagram at the side. Okay, refer to this thing and tell me what are the boundary conditions. Again, your x 0 is here. Okay, so this is like this. Okay, this is y, this is x. Tell me. At x equal to 0, we have w is equal to what? Not w, sorry. Y equal to how much? At x equal to 0, y is equal to
0.
Y equal to 0. Okay. What does that give us? If you just substitute here. So that is b plus d equal to 0. Okay. At x equal to 0, at x equal to 0, we have what? Moment is equal to 0. Okay, so m is equal to 0. M equal to 0 means you have to differentiate this twice. Okay, which means that so let's do this. So dy dx is equal to what? AK cos kx minus bk sin kx plus c, and this thing is d square y dx square is equal to minus ak square sin kx minus bk square cos kx. All right, so we actually have to multiply this with ei all throughout, but the good news is that this is m is equal to 0. Okay, so we can quickly write this down as so implementing this condition, what we have is, if you set x equal to 0 here, you what do you get from here? B equal to 0. Is it not? So basically you are obtaining this thing. So please check if this is correct. I'm only doing myself. Please tell me if this condition is correct and this condition is correct or not.
Yes, sir.
Yes or no?
Yes, sir.
Okay. Next, at x equal to L, what should we use? Again, I'll copy this thing here so you can quickly refer. Tell me at x equal to L, what condition should I use?
Y equal to 0.
Y equal to 0. So this is a sin KL plus b cos KL plus CL plus d equal to 0. And at x equal to L, what other condition should I use at x equal to L?
dy dx equals to 0.
Dy dx is equal to 0. Okay, so we have already have this expression for dy dx. I'll just copy this thing. So at x equal, this thing becomes ak cos KL minus bk sin KL plus c is equal to 0. Okay, so and earlier we have obtained that b plus d is equal to 0 and b equal to 0. So you tell me from here, if b equal to 0, d is also equal to 0. Okay, so this becomes a little bit simplified. This b also goes away, this b also goes away. What are we left with? So from here, let's just see. We obtain a sine kl. What is left? B is going away, D is going away, plus CL equal to 0. And then from this one, what we have? AK cos kl, this B goes away, plus C is equal to 0. Okay, so what can we do from here? Tell me. So this can be written as A sine KL is equal to minus CL, and this can be written as A K cos KL equal to minus C. Does that help us? We can divide these two things. Okay, so let's say this is 1 and this is 2. We divide this thing. What do we obtain? Tan KL divided by K is equal to L, and which gives us tan KL is equal to KL. Okay, so this is the condition. Now, let me just write this thing. So this is neither an algebraic equation, not a differential equation. What kind of an equation is this? Tan KL equal to KL. This is a transcendental equation, okay? And you cannot solve this by hand. Okay, so in earlier days, what people used to do is, maybe from your JEE days you have done these things, okay? I mean, this used to be a common type of questions back in our day. So basically, you have to consider this as a function and this as a function, and you plot this thing and you plot this thing wherever these two things intersect. That is the solution. Okay, so that is what is the geometrical meaning of this equation. You have a function tan KL on the left hand side and you have a function KL on the right hand side. Wherever those two functions are intersecting, that is where this equality is holding. Okay, so I mean, you can do like that, and you will find out that the solution for this thing is true when KL is equal to something like 4.4934, something like that. Okay, approximately 4.5. Now, please note or please compare with what we had obtained earlier. Okay, in the previous problem, we had obtained this KL is equal to pi by 2. Now, it seems very beautiful, but it is just like this. This KL is equal to pi by 2. Now, pi by 2 is just a number. Okay, this is 3.141592653, something like that, divided by 2. There's just a number on the right hand side. In the previous case also, case number 1, here also you are obtaining this KL equal to n pi, or basically KL equal to pi. Okay, for this n equal to 1, you are getting k equal to pi. And then that is also KL equal to 3.14159265358 and like that. So in terms of the maths, there is not much difference between what you were getting earlier and what you are getting now. That was just a number. This is also just a number. KL equal to something you are obtaining. Okay, so just like before, you can go about determining the value of the P critical here. Okay, please also note that this KL equal to 4.4934 that we are obtaining, this is only one of the solutions. You will also obtain this equality for higher values of KL. Okay, so for instance, you just note that this is so something like this, right? Or our graphs for tan x, it is something like this, and then this So if you consider the KL like an X, or this thing, this KL also like an X, so you just have to obtain the intersections where this is occurring. So if you have one intersection here, you will have another intersection here, things like that. Okay, that's what I mean by you will have multiple solutions. I'm only considering the lowest solution. Now, when you consider this, then your P square by EI, your P by EI becomes what? 4.4934 divided by L whole square. Okay, so earlier in place of this thing, you were getting pi or pi by 2 or something like that. And now you have this strange looking number, but it's just the same thing. Okay, so you will also obtain a P critical from here also. Okay, so this P critical will come out to be approximately 4.5 square EI divided by L square. Okay, and just like before, when you were able to obtain L effective, you can find an L effective here also. Okay, so how can you find an L effective here? Well, you can do like this. You can consider this to be pi square EI, and then consider something like this. So does this make sense? What I've just written? Well, you have to adjust with a pi square also. Where do I put the somewhere here? Okay, so I hope this is perfectly equal to this thing. Okay, so the L effective will be what? Will be pi L divided by 4.5. Okay, approximately. Does this make sense? So please think about it a little bit. If you have any doubt, tell me, because I am going to ask you to do something as a homework next. Whatever I have done, does this make sense? Okay, you don't have to say yes or no right away. You can think about it. What I'm going to give you as a homework is this thing. Okay, another case. So this will be the case of a clamped end. Please note that there is no pin joint to this guided support now. Rather, it is a clamped end. So both ends are clamped. So this problem also has been done in Beer and Johnson through some kind of analogy and hand waving. And if you read through it, you will, I mean, if you're a little bit mathematically oriented, you will feel, I mean, there's quite a leap of faith involved. Okay, they are talking about some inflection point and something through some arguments. It's filled with words. But I think if you proceed in a systematic fashion through a fourth order equation, you should be able to obtain. And what you have to do is at x equal to 0, you have to impose the condition that y equal to 0 and dy dx equal to 0. And at x equal to L, similar conditions, y equal to 0 and dy dx equal to 0. So please try to do this thing and try to get a condition. Okay, mind you, in the last few steps, you have to unleash your JE level algebraic manipulation skills to get a neat and clean solution. Okay, but it's quite fun to do it. Okay, I'll of course show this thing myself also, but try to do this thing on your own. All right, so because we have had just 2 lectures this time, I'll try to record something and share with you. Okay, so that's the end of this class. Thank you very much. We'll try to begin with our last chapter, on energy methods in the next week. Okay. So thank you very much. You can go to your next class. And if you need to ask, yeah, thank you very much, everyone. You're absolutely free to go to the next class. If you want to ask something, I'm here for a couple of minutes more.
Sir, as only last topic are left, so can you do the live session only for the instead of recorded lecture?
Actually, energy methods, ideally it requires something like proper solid 2-3 weeks. Okay, that's why I want to invest more time on that. Okay, but if I see that I am reasonably able to finish the energy methods thing, I will come back to buckling and take a live session for buckling. Okay, maybe 1.5 hours or something like that. Okay, let me see how it turns out.
Thank you, sir.
Yeah.
Okay, thank you, sir.
Actually, next week also we are going to lose one class on Thursday, I think. November 4th is a holiday, right? Because of Diwali. That's an institute holiday. All right, guys, please go. Thank you. And well done on the overall performance in the test too. I mean, we set slightly easy questions, but the fact remains that you were able to do much better than the first test. So well done.
Sir, actually the month of November, sir, is quite loaded, sir. So will we have both the assignment and the test in that month, or will you give it earlier?
Which one? And the November month is quite loaded now.
Yes, sir.
Okay.
Yes, sir. I mean, we have like each subject has one assignment and one test or 1 or 2 tests.
Yes.
Yes, sir. If you
Let me
could
see.
look into that, sir. Yes, sir.
Let me see what I can do.
Yes, sir. Yes, sir. Okay, sir. Thank you.
All right. Thanks.